All right, it's 8 o'clock. Unless anybody wants me not to, I'll go ahead and start. My name is Dan Biederman. I'm here to present, how precise time can make AI workloads more efficient. And I had a lot of help with this. You can see lots of people at Intel have helped contribute to this. And so the agenda today is we're going to talk about a brief history of time, talk about traffic and on-time arrivals, constructing the time machine, use cases, talk about Gen AI and precise time, and can we precise time everywhere. So I wanted to go back and look at history, and different people have different opinions of history, but this is mine. If you look at, back in the 80s, right, that's when they started doing NTP. They needed a basic way of doing timekeeping. And so, back then, millisecond or, maybe hundreds of microseconds were okay. But over time, the software delays and the queuing delays in the network became, difficult for other applications to use it. So the industrial, and energy group got together and created IEEE 1588, the first version of it, which did hardware timestamping and, pushed this precise time, further. In 2008, there was a release of the next version of IEEE 1588 that had telecom, and telecom pushed it. And video, audio, video, and a lot of other things started taking advantages, such as the Internet of Things and audio. In the last decade, the data center has started to consume IEEE 1588 in precise time. And I want to highlight some things. One, Kevin Stanton's here with PCIe PTM. That was, in products. And then we also had instructions such as tpause and the start of OCP tap, which looks at precise time in the data center. And, Meta published a paper in 2022 about how you could get databases to run 100 times better, reducing that window of uncertainty. And there are other service providers or cloud service providers that have shown similar results. And finally, we have, in 2024, the start of Workstream 10, which is looking at not only AI and ML and how precise time can work at it, but other technologies as well. And so going forward, you have different things, pushing it. Right now, I think the thing that's going to push precise time is artificial intelligence and machine learning. So let's talk about precise time. It's kind of like the last frontier in, this concept of computing we call time coordinating computing. So, what do you need? Being from Intel, a lot of this is Intel focused, but there are lots of other components, that are available for people to use. But, you basically need three types of components. You need the hardware timestamping, which is like the PCIe PTM and the IEEE 1588. That way you can get, precise time to the application itself. And then you have instructions like tpause and timed GPIO, which allow you to do things at precise times. Thus, the application can now be precise time aware. And you also need the software, the PHC2sys, Python libraries, Linux initiatives, and one-way congestion control. So let's build a time machine. So what are the ingredients? So you need hardware. You need a processor or an XPU that basically can handle a precise time, such as the Xeon, Gen 5, Gen 6, which supports tpause, PTM, and these kind of things. You need NICs or IPUs that can support not only 1588 on the Ethernet side, but PTM on the PCIe side. And finally, you need high-quality board components like crystals that will give you the precise clocks you need. One thing at Intel, we've been doing precise time for a long time. We've put a lot into 1588 back when the telecom companies were using it, and we've just grown that since. We've contributed a lot to PTP4L, and basically we have things in Linux as well as drivers that you can take advantage of. The one thing that I'm going to talk about today, software-wise, is time APIs, and how we're moving that forward so it's easier for people to use precise time in their applications. So recently we had the following setup in our lab. We've got a lab in Europe and a lab in the US where we're trying to basically see what we can do with precise time. And as Chris Hall has shown before, you can get tens of nanoseconds of jitter under load when you have precise time, or PTM, and this is seen at the processor, versus if you have a load, you're going to get significant jitter. And this is with our E830 NIC. So use cases, there are lots of use cases. We could talk about telecom, we could talk about microservices, we could talk a lot of things. These are some that I think are important to the data center. One of them is databases. Major cloud service providers have already used precise time to make their databases work better. Video, to me, video is a lot like AI. You have very bursty data patterns, and you can use precise time to handle those bursty data patterns much better. And there's standards like SMPTE 2110, the Society of Motion Pictures and Television Engineering, and they use precise time to reduce incast and to reduce the handling or the cost of the equipment. And Intel has contributed to the media library so that it's easier for people to have their video applications. Gaming or cloud gaming is something that could be very interesting in the future. You have AR, VR, you have joysticks and stuff like that. With precise time, you can have certain events appear at a precise time. You can also click who touched the button first and how they reacted to it, and store that and then take that back to the cloud gaming server. And it really doesn't matter if you're a kilometer away or 100 or 1,000 kilometers away, because the precise time could be used to mitigate the issues with the distance. High frequency trading and the trading firms, with precise time, you have the ability to display information, as I mentioned earlier. So if the US government wants to give a jobs report or something like that, instead of being close to Washington, D.C., they can make it such that it decrypts at a precise time, so everybody sees it. All the high-performance computers could work on it at the same time. And finally, what we're here for today is Gen AI, right? With the workloads that we see, they have a lot of microbursts, lots of incast, and they have latency issues, right? If we can use precise time to coordinate all-to-all or any-to-any traffic, then we can basically improve efficiency, help with the interactions, and reduce the max power, which is a major pain point of the data centers today. So let's talk about a little bit more about Gen AI and how it could help. So similar to video, which is very bursty, you'll see these bursts comes out every time a frame is captured. They want to send the frame as quickly as possible. The same thing is true for AI, right? Up at the top is a presentation that was given a couple OCP global events a couple years ago. And basically they show the ideal situation for a 200 gig flow is a bunch of flat lines, right? Everybody has the same amount of bandwidth, and it's pretty evenly distributed. But what you actually see is that it's like a sawtooth pattern. Basically, you go above the max bandwidth, and then you have to send a pause frame, or you have to send a drop a packet. And if you do all these things, it hurts latency, it hurts the data flow, and it hurts the performance of AI. And so, basically, with precise time, we can attack those large buffers. Because that's another thing that they do is they'll just use more expensive switches, just like video did, and video, tried to remove those large buffers. And so, these issues can lead to large latencies, that you can have incast issues, and if it goes out to an external buffer, it could have significant power issues. So I'm part of Workstream 10. I'm helping to lead Workstream 10. And there we're actually looking at, in one of the groups, how AI and precise time can work better together, right? And so we've been looking at doing simulations, and we believe there's at least a 40% upside, or at least that's what we're targeting, to using precise time to make AI and ML better. So earlier I talked about APIs, and the good thing about APIs is that if you can make an API, people can just include it, and all of a sudden things become time aware. So if we have a Python API, the great thing about this is pretty much anybody who's written something with, like a PyTorch application for AI could now make it time aware. And so there could be benefits for that. You could have real-time AI or a better understanding of how you're processing things with regards to time. It could allow for pacing, and it could allow for power savings. You could also use it for other things that are not AI. You could use it for game controllers. You could use it for robotics, or you could use it for real-time testing. And so can we precise time everywhere? It's important for us to look at how precise time has worked in the past, right, and how it will work in the future, or help us in the future. Video is a great example of, they had large incasts, they had large issues with regards to bursting and microbursts, and they solved that problem with precise time. Now we could do something similar. We have 1588, we have PTM, which can go directly to the processor. I've talked about many use cases here, and we can use that precise time to, as I mentioned, reduce latency, reduce incast, and probably one of the most important things is to reduce power. So if you leave with anything today, this concept of precise time and time-coordinated computing, that is computing or AI that uses precise time, can help you reduce your max power consumption. Thank you. Any questions or comments? Oh, yes.
Yeah, so OCP NIC, does it also support precision time?
OCP NIC supports it, right?
So it's interesting that you didn't mention that in your presentation. You talk about Intel NIC and all that. Just observation.
Yeah. I mean, I think I did mention that there are lots of products that have precise time. And so 1588 has been around for, since 2002, so there are lots of NICs with it. The PTM is the new part, so there are only a selected few. And there is a PTM, the workstream 9 keeps track of all the different PTM-capable NICs. And so, do you have a question?
Yeah. Can you help me visualize to understand how time helps? I'm kind of thinking of job completion time, where the tail latency is what matters, so the whole cluster slows down to the slowest guy. So how does it help to put everyone
So
as
what causes that tail latency, right? What causes the tail latency is the burstiness of the traffic, right? So the ideal flow would be something like they showed, I think it was 2025, or not 2023, but basically you want all the ideal flows to be the same, right? But when you have these burstiness, it could cause a retransmission, or it could cause a pause. And what does that do? That basically delays the packet, or it forces a retransmission of that packet, which will cause you large tail latencies. Does that make sense? So ideally what we want to do is we want to take that kind of like sawtooth wave, cut off the peaks, and invert it through pacing or some other method. And that's what video has done with all the different AVB and TSN technologies that they had. And we just need that for the data center, where we can take advantage of precise time to clip off those peaks, reduce the incast, and with that, you should reduce latency.
So. All right then.
Good?
We'll go for the next one.
All right.
Thank you.
Thank you.